In Lesson 5, we learned the gradient, divergence, and curl operators. Divergence measures how much a vector field spreads out from a point. Curl measures the rotation of a vector field at a point. In Lesson 6, we mastered coordinate transformations and scale factors. Now we connect these operators to two powerful integral theorems, the Divergence Theorem and Stokes Theorem. These theorems bridge local behavior, what happens at a single point, to global behavior, what happens over an entire region. The Divergence Theorem, also called Gauss's theorem, states the surface integral of A dot ds over a closed surface S equals the volume integral of nabla dot A dv over the enclosed volume V. Think of it this way. Imagine a closed surface, a box, a sphere, any shape. The total flux flowing out through that surface equals the total source strength inside. If divergence is positive somewhere inside, that region is a source pushing flux outward. If divergence is negative, it is a sink pulling flux inward. You don't need to check every point inside. Just measure what comes out through the surface and you know the total. Let us verify with an example. Let A equal x squared e hat x plus y squared e hat y plus z squared e hat z. We integrate over the unit cube from 0 to 1 in each direction. First, the right-hand side. The divergence of A is 2x plus 2y plus 2z. The volume integral over the unit cube, integral of 2x from 0 to 1 gives 1. Similarly for 2y and 2z. Total 3. Now the left-hand side. We evaluate the surface integral over all 6 faces. On the face x equals 1, the contribution is the integral of x squared over that face, which is 1. On x equals 0, the contribution is 0. Similarly, for the y and z faces, adding all 6, 1 plus 0 plus 1 plus 0 plus 1 plus 0 equals 3. Both sides equal 3. The divergence theorem is verified. Stokes' theorem states the line integral of A dot dl around a closed curve C equals the surface integral of curl A dot ds over any surface S bounded by C. Think of it this way. Walk around a closed loop. The total circulation, how much the field pushes you along the path, equals the total curl passing through any surface stretched across that loop. The remarkable thing, it does not matter which surface you choose. A flat disk or a curved ball, as long as the boundary is C, the result is the same. Let us verify with an example. Let A equal minus y e hat x plus x e hat y. Take C to be a circle of radius r in the xy plane. First, the right-hand side. The curl of A, the z component, is partial x over partial x minus partial of minus y over partial y, which is 1 minus minus 1, giving 2 e hat z. The surface integral of 2 e hat z dot ds over the disk. Since ds points in the z direction, this is 2 times the area, which is 2 pi r squared. Now the left-hand side, parameterize the circle. X equals r cosine t, y equals r sine t. Then A dot dl equals minus y dx plus x dy, which simplifies to r squared dt. Integrating from 0 to 2 pi gives 2 pi r squared. Both sides match. Stokes' theorem is verified. Let us compare these two theorems side by side. The divergence theorem converts a closed surface integral into a volume integral. The operator is divergence, nabla dot A. It answers how much flows out of a closed surface. Stokes' theorem converts a closed line integral into a surface integral. The operator is curl, nabla cross A. It answers how much circulates around a closed curve. Notice the pattern. Both theorems relate an integral over a region to an integral over its boundary. The divergence theorem goes from 3D volume to 2D surface. Stokes' theorem goes from 2D surface to 1D curve. These are not just mathematical tools. In electromagnetic theory, Gauss' law for the electric field is the divergence theorem applied to E. The flux of E through a closed surface equals the enclosed charge divided by epsilon 0. And Faraday's law is Stokes' theorem applied to E. The circulation of E around a closed loop equals minus the rate of change of magnetic flux. So these two theorems are the mathematical backbone of Maxwell's equations. Let us review. The divergence theorem relates a closed surface integral to a volume integral through the divergence operator. Stokes' theorem relates a closed line integral to a surface integral through the curl operator. Both convert between a region and its boundary. In the next lessons, we begin electrostatics, where these theorems become the foundation of Gauss's law and Faraday's law.